So in fact, he'll be talking about recursive mutexes and separation logic. Thanks.
Thanks, Ben. All right, so so I told you guys this morning about the work we've been doing on program verification for hypervisors. And this isn't about hypervisors, but it's still about C++. And it's still built on this brick program logic. So when we originally built brick, we built it to do the verification of this hypervisor platform. And we talked about the concurrency and all sorts of stuff like that. Lots of interesting questions written in C++, but mostly standalone. And in this talk, I'm thinking about, how do we go from this standalone kind of low-level systems code and move it into kind of more mainstream C++, thinking about more generally embedded systems or device drivers, robotics, server infrastructure, and things like that. And the main thing that I'm going to talk about in this talk is the fact that one of the big differences between this is basically freestanding. We didn't use a lot of the standard library. We kind of coded things to keep them simple, so we could do verification on them. And you go to people who do C++ for real, like maybe the people who work at Bloomberg, and you tell them, sorry, you can't use any libraries. You have to code everything from scratch, and they'll probably just tell you to go away. It's not worth it. What's the point in using a language like C++ if you can't use the millions of lines of code other people have used? So in this talk, I'm going to be thinking about the fact that to kind of expand to the real world of C++, we need to support things like the standard library. And in this talk specifically, I'm going to talk about this very tiny, tiny, tiny sliver of the standard library about mutexes. And mutexes are interesting. This is work with William Mansky and Kedu at UIC, and they are interested in kind of verification of concurrent algorithms. And we just decided, well, let's start with mutexes. Those should be simple enough. So this is the mutex specification, kind of. This is from cvpreference.com, I think. But mutexes are kind of like locks. I'm assuming that people basically know what a mutex is. But the idea here is that a calling thread will own a mutex. So you can't pass threads around, or you can't acquire a mutex in one thread and then release it in another thread. And there are some other rules in here, like mutexes can't be destroyed while they're locked and things like that. So we wrote a specification using brick for these, and I'll give you kind of the highlights of this. I'm going to note that this is an axiomatized specification, and when we look at specification of the standard library, there are some things that we can verify, but the implementation of mutex is actually very low level, like send signals on these things and stuff like that, and so we're not really focused so much on the actual verification at this level. We have done some proofs in this work, and I'll tell you about them later. So in separation logic, we're going to have a predicate called mutexR. That's ownership of this mutex, and it's going to protect this invariant P. And then you've got a locked predicate. This is pretty standard stuff from separation logic. And using that, we can write specifications like the specification for lock and unlock. And here you can see that we're capturing this characterization that the current thread owns it by adding the thread that did the locking on mutex.locked. And so when you get it back, when you acquire the mutex on a particular thread, you take the current thread and you use it here. And then when you unlock, you're required to be unlocking from the same thread that you're on. Okay? So you can technically pass the mutex.locked token to another thread, but they won't be able to call unlock because their thread ID will be different than your thread ID. Sorry. All right. Maybe I've lost people. But you can see basically the strategy here. The beautiful thing about separation logic is even complex concurrent data structures look relatively sequential. All right, so we can do the normal sort of, when you acquire the lock, you get access to the resource. When you release the lock, you lose access to the resource, but you're required to reestablish them. Okay, so it's the nice part about separation logic. All right, so we can use this to verify a very simple program. And I realized I cut out some of the thing, but this is a simple class C. It's got two longs, an A and a B, and they're guarded by a mutex. And they've exposed methods like update B and update A, which acquire the mutex, increment or decrement the value, and then unlock the mutex. Right? So this is a program you can specify it. This is a very simple spec for it. Not really any problem here. Okay. Now, if you go and you add a transfer function to this, you might say, okay, what we want to do is we want to make sure we'll take the lock here, then we'll update A, and then we'll update B, and then we'll unlock. And we'll know because the amount of money or whatever that we're putting into A is the same as the amount of money that we're taking out of B. and everything should all work out really well. And you could actually verify this. It would be a nice and simple proof. But the problem is that in the real world, you'll actually get a deadlock here. You already own the mutex, which you acquired on this line, and you're reacquiring it here. Because we care about safety, it's not a problem for our proof, but it's really a problem for the implementation. And the way this is addressed in some systems, including Java, for example, is to use something called recursive mutexes. So the interesting new thing about a recursive mutex is you acquire a mutex. If you acquire it again, then instead of deadlocking, you just say, OK, you have it. You didn't need to do that. So you can lock, and then when you unlock here, you don't give up the resources. You get to keep them. So no one else can come in and grab here until you do this unlock here. So when they say recursive mutex, it's like lexical locking. And this is the concurrency primitive that underlies the implementation of synchronized in Java, which I did many years ago, but I haven't done lately. OK. I'm sure I've lost some people at this point. I apologize for that already. You can take the implementation of C and change mutex to recursive mutex, and then this code works out fine. OK? So now you're not going to see a deadlock when you try to update A here, because this lock will not deadlock you. You'll just increment this counter. And we can then verify this. And now the question is can we write a specification for recursive mutex that looks and feels like mutex in the way that people are used to? Hey, I've got a mutex. Let's just change to a recursive mutex so I can handle these new patterns. And what does that actually look like? So here I've got the mutex specification above, and here's the recursive mutex specification below. There are a few lower level details that are changing, but I'm going to say at some level these things are quite similar. One thing that's slightly different about this is an axiomatized characterization directly. We're actually proving this specification holds from a lower level atomic update style specification. So because I presented this in an invariant guarding style, I wanted to show this in the same style. So this is actually a derived specification on top of a slightly lower level specification. Now, for regular mutexes, the two are equivalent. You can prove one from the other in both directions. For recursive mutexes, I think it might be it's at least an opener question to me. I haven't considered if you could actually verify in both directions because of the recursive nature of these things. All right, so we again have the recursive mutex ownership. That's the sequential ownership that we'll share amongst threads. And now, instead of having a single locked predicate, we're basically going to say everyone who's interested in using this recursive mutex needs to have a holds predicate. Okay? And that holds predicate is kind of poorly named, but it says this thread holds that mutex n times. If I don't hold the mutex, I'll hold it 0 times, and that's perfectly fine. But as soon as I start acquiring it, this n will go up, and then it will behave a little bit more like locked. So I already said that. So basically what we're doing is we're taking the kind of Boolean that we think about here. It's either locked or it's unlocked. We're generalizing that to a natural number where 0 means it's unlocked, and then successors mean it's locked with so many times, I guess, to say. And we can use this sort of borrowing lemma that says if you actually hold the lock, then you can grab this holds thing, and you can actually get P out. That's where I'm actually going to be able to get an access to P. And then I can put it back when I'm done by reestablishing P. And so you can see a little bit here how this might work. If you acquire the mutex originally, you might figure out, maybe you wrote a 3 into that value. You'll acquire the mutex, then you'll borrow the stuff out. You'll get access to this. You'll maybe update to 3. Then when you unborrow, you reestablish the existential quantifier. And then if you try to borrow again, then you'll lose the fact that you wrote 3 here. Okay? And so that's a problem, because when you think about that initial program, I called in and I acquired the lock. Then I did the update, and I kind of released the lock at the end of that. That would normally require me to unborrow, but then I would lose the information that I had. So we have to fix this. We have to make it so that borrowing and unborrowing is kind of information preserving. And the way we capture this is to extend this n. So we used to have n here, which is the regular natural number. But what we're going to do is we're going to take the p here, which is usually just an empred, and we're going to expand it by basically the existential quantifiers that are available. So rather than this being just, a prop or an empred, it's going to be a function from number to empred. And then the numbers that fill in those holes are going to be stored in this args when the value is actually locked. And that allows us to make this borrowing lemma here, which says when you borrow, you get the p at x's, and then you can get it back. And there's another update lemma that allows you to actually change the value of x's here. So now, when you unborrow, you basically get something like this. And then by basically delta reduction, you can get back. So now we can go back and forth. We can go in and out without losing any information. And that allows us to write a specification for something like update. Update A or update B are basically equivalent. It says, I hold the lock here. Sorry, I might hold the lock at the beginning. I don't know. I've got args, but args could be 0, so I don't hold it at all. At the end, it's still a valid lock, and I'll still hold it with the same args, so the same distance, but I will, sorry, not with the same arguments, but the same number, the same depth of acquisition. But I will have updated the model in this particular way. And this allows me to acquire the lock on the outside and then figure out what updates occurred without having to, this is allowing us to expose those existential quantifiers. And this also allows us to prove a stronger transfer specification, which is the one we wanted. So what did we actually prove here? We proved update A and update B, and we proved transfer up to a little bit of overflow. And we proved these against this resource specification that I showed here. And we proved the resource specification against this logically atomic spec. The interesting thing about these proofs is that none of these proofs require separate case analysis on whether or not the lock was originally acquired or not. Okay, so it really does, the proof still feels very much like a mutex proof, a regular mutex proof, rather than having to reason about the two cases independently. So that's it for the talk mostly. This is us. And the development we're doing is here. The standard library specifications is an open source project. So you can take a look at the specs we've written so far. We're trying to build this out more in service of people who are interested in doing program verification with C++. So we've got things like CC types and assert and several other libraries. We've got someone working on shared pointer right now, which is kind of interesting. And the brick program logic and the automation documentation, if you're interested in any of that. And that's all I have until my next talk. Questions?
Questions?
Thank you. This may be a bit off topic, but I noticed you have this thread resource in your specs, and I was wondering if it is somehow not transmissible from one thread to another, which would not make sense.
It is not transferable to other threads. Yeah.
Okay.
It is a subjective thing, and it's done with
Okay.
monpred.
Thank you.
Thanks. More questions?
Go ahead.
I was wondering whether there was any deep reason why you merged the current acquisition count with the other stuff basically in this access predicate, because it seemed like, then you have to tease it apart again in the spec, and you also were updating one but not the other, which I guess would be you have to tease it apart again for this lemma, which lets you switch between held and holds or whatever it was, and here you have to update just one field. Like, it seems like usually these would be separate, or I don't know.
There is some tying between them, because if n is 0, you don't actually have arguments. You can get them, but they don't mean anything. So the type of args is actually like 0, or successor of something and this other thing.
Ah, I see. Interesting.
Yeah.
Okay.
Otherwise, you can't get this property exactly. Well, you can because you know args is inhabited, but it doesn't work out as nicely. You still end up with other stuff.
Okay, I understand. Thanks.
Time for one more question, if there are any. Well, if not, let's thank Gregory for a second time.
Thank you, Ben.